reduces the amount or the number of gaseous molecules converting into the gaseous phase. Right? So what happens? You can see only few gas molecules are there, hence the vapor pressure also will be less. Now the intermolecular interaction between AA-BB will be equal to AB. Herein the AB interactions are not same with the AA and BB interactions. So once a solution is formed, the interactions is more. AB interactions are more means the molecules are held together. That is, the solute and solvent are held together very closely. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I'm back with session 4 of the chapter Solutions. So in the last session we discussed the solubility of gas in liquid, wherein we studied the important laws, that is Henry's law, and the application of Henry's law also we studied. And then later we moved on to the vapor pressure of liquid solution, wherein we studied another important law which is called as Rolle's law. Right. So in today's session, we are going to study the vapor pressure of solid in liquid solutions. Okay, solid in liquid solution, as well as what is ideal and non-ideal solutions and what are azeotrophs. Clear? So we are going to study what is vapor pressure of solid in liquid solutions. So according to Rolle's law, for a solution, the partial vapor pressure of each component is directly proportional to its mole fraction. Rolle's law we have already studied. So what is this vapor pressure of solid in liquid solutions? So already we have studied vapor pressure, that is the pressure exerted by the gas phase on the liquid phase. So you can see here in the first diagram, you can see it is just the pure solvent which is present. So let us consider the component A. Only component A is present here, and what is happening? Yes, the gas will be starting to evaporate, and what happens? These are the gas molecules which you can see, and the pressure exerted by the gas on this liquid surface is called as the pure vapor pressure of the component A. That is, you can say P0 A. Right. Now, this is in the case of the pure component A, that is no other components are present here. Now, what happens? A solute is being added here. Which is the solute? The solute is a solid in this case. It's a solid in liquid solution. So, this is a liquid, only A is present here. Now, let's assume that we are adding a component B. Now what happens? The green colored balls you can see, those are those of the solute, the solid solute which we have added. Now once the solid solute is added here, what happens? It will remain in the surface of this liquid. So what it will try to do? It will try to reduce the amount of or the number of gas molecules getting converted into the vapor phase. It will remain in this liquid surface, and what will happen? The vapor pressure also in turn will decrease, right? So what we can conclude from this, when the solute or a solid solute is added to the liquid solution, what will happen? The vapor pressure will decrease. Here itself you can see, here are more number of gaseous molecules are there. That means more vapor pressure will be there. Now once the solute is added, you can see the green balls are occupying, that is your solute is occupying the surface of the liquid, and what happens? It reduces the amount or the number of gaseous molecules converting into the gaseous phase. Right. So what happens? You can see only few gas molecules are there, hence the vapor pressure also will be less. So once the solid solute is added, what will happen to the vapor pressure? The vapor pressure of the liquid will decrease. I hope it is clear. Right. Now, the binary solution of the volatile liquids can be classified into two types. So there are two types of solutions that we have to study. One is ideal solution and non-ideal solution. So what is ideal solutions? Let us see. Ideal student or ideal solution. We generally say ideal student. What does that mean? It obeys, or that person obeys, or that student obeys all the rules and regulations of the institute, right? He's good at studies, he's good at sports, dance, music, everything. A very good ideal student, right? The same way, ideal solutions are those solutions which will obey a set of rules. So what are those? Let us see. A solution which obey Rolle's law at all concentration range is called as an ideal solution. So Rolle's law we have already studied, right? P1 is equal to P1 not into chi1, that is partial pressure is directly proportional to the mole fraction. So this Rolle's law obeying solutions are called as ideal solution, and it must obey in all concentration ranges. Any concentration, that solution must obey Rolle's law, that is called as an ideal solution. Now example, benzene and toluene. chloroform and bromobenzene solution, normal hexane and normal heptane. So these examples also you have to remember. So in an ideal solution, delta mix H is equal to 0 and delta mix V is equal to 0. Now what does this mean? So there will be the pure components. Let us assume you will have a solute and you will have a solvent, right? So there will be a pure solute and there will be a pure solvent. These two will mix together and form the solution. So in this case, you are only having the solute, and in here you are only having the solvent, and in solution you have both solute and solvent. So once you are mixing these two, right, there will be a heat evolved or heat absorbed, right, and there will be no change which is happening. That is, the heat will be 0. The enthalpy change will be 0 initially, and after the solution is formed, the enthalpy change will be 0 in case of ideal solution, as well as there will be no change in the volume also once the solution is made up. I hope it is clear. Now, an ideal solution, solvent-solute interactions are equal to solute-solute interactions and solvent-solvent interactions respectively. That means that, let us see here, initially the solvent is only present, that is A, right? So there will be interaction between A and A. The solvent is A means in this whole beaker you are only having A. So all this A will interact with each other, that is called as your AA interactions will be only present. Now coming on to the solute, only solute-solute interactions will be there. That is, BB interactions will be only there. Now what we are going to do is, we are going to mix the solute and solvent. So you will get AB, that is your solution. So in AB what you are having, you will be having AB interactions. So in an ideal solution, AB interactions will be equal to AA interactions and BB interactions, right? Now moving on to non-ideal solutions are those solutions, of course, which does not obey Rolle's law at all concentration range. Okay, ideal solutions will obey Rolle's law in all concentration. Non-ideal solutions will not obey Rolle's law at all concentration. Some examples are HCl and water, ethyl alcohol and water, ethanol and acetone. So in this case, the change in enthalpy and change in volume will not be equal to 0. In case of ideal solution, it will be equal to 0. That means there will be no change in volume or enthalpy. But here there will be a change in enthalpy or volume. The force of attraction between A and B molecules will be greater or lesser than that of AA and BB interactions. So same way we can see here, AA interactions will be there between solvent and solvent. BB interactions will be there between solute particles, and AB interactions will be there between the solute and solvent in the solution. So in an non-ideal solution, AB interactions, that is this interactions, will be either greater than or lesser than AA and BB interactions. It will not be equal like in ideal solutions, right? So let's differentiate between ideal and non-ideal solutions. Let us summarize what we have discussed now. They should obey Rolle's law, ideal solutions. Non-ideal will not obey Rolle's law. And here the change in volume and change in enthalpy will be equal to 0, and in there it will not be equal to 0. Now the intermolecular interaction between AA, BB will be equal to AB. Herein the AB interactions are not same with the AA and BB interactions. Clear? Now, non-ideal solutions, they are further classified into two types, that is non-ideal solution with positive deviation and non-ideal solution with negative deviation. Okay, so let's understand the first one, that is non-ideal solution with positive deviation. The solution for which the total vapor pressure is higher than that of an ideal solution of same composition and temperature are called solution with positive deviation. The solute-solute and solvent-solvent interactions are stronger than solute-solvent interaction. So what does this mean? Let's see. So this graph we have already discussed while we were discussing the vapor pressure part, right? So in this case, what you have to see, as you know that initially this is the pure component A, and here it is just the pure component B. Now what happens as A and B is combining or forming the mixture, what will happen? The vapor pressure will start decreasing for A, and the vapor pressure will decrease for B as well. Now what happens? This is the P total that you can see. P total, which is equal to P1 plus P2 or PA plus PB. Now what is happening in case of non-ideal solution with positive deviation? The total vapor pressure, that is this line, will be above. You can see this is the total vapor pressure now for an positive deviation. That means originally what it is supposed to come, more than that there a deviation you can see. Here you can see the deviation will be more. That is a positive deviation. Now why there is a positive deviation? The reason is because the interactions. That means we have already studied here in solvent there is AA interactions, right? In solute there is BB interactions, and in solution you have AB interactions. So now when your AA and BB interactions are stronger, that is AA and BB interactions are stronger than AB interactions, positive deviation will take place. Now why is that? AB interactions are weaker. AB interactions means when the solution is formed, the interaction between solute and solvent is weak. Solute and solvent interactions is weak means easily the vapors can be formed, right? Interactions are less means easily from the liquid phase, gaseous phase can be formed, right? So more number of molecules will be evaporated. What will happen? More vapor pressure will be present, right? That is why you can see a positive deviation here. I hope it is clear, right? So let PA will be the partial vapor pressure of the component A, PB is the partial component vapor pressure of component B, and delta H and delta V is the change in enthalpy and change in volume. So I hope that is clear. Why this positive deviation is taking place is also clear for you, right? Now for positive deviation, PA will be greater than PA naught into chi A, that is according to your Rolle's law, and PB will be greater than PB naught into chi B. It will not be equal, it will be greater. And delta H and delta V will be also greater than 0. So total vapor pressure is more than expected from Rolle's law. Total vapor pressure, you can see the total vapor pressure is more than which is expected. So example is solution of ethanol and acetone. So it is important to remember one example as well. Now non-ideal solutions with negative deviation. Okay, so from here itself you can see negative deviation, you can see this is the expected one from the Rolle's law. That is, this is the expected P total which is supposed to come. Now, the vapor pressure of the solutions, once the solute is being added to the solution, what happens? The vapor pressure will decrease. You can see here what happens. It is decreasing here. The P total is decreasing, right? So this is a negative deviation you can see. Now why is this negative deviation happening? As discussed, AA interactions are there, BB interactions are there, and once a solution is formed, AB interactions are there. So in this case what is happening? Why negative deviation? AB interactions are stronger than AA and BB interactions. So once a solution is formed, the interactions is more. AB interactions are more means the molecules are held together. That is, the solute and solvent are held together very closely. So it becomes difficult to break the bonds and convert into vapor phase. Hence, the vapor pressure will be also less. That is why you can see a negative deviation here. I hope it is clear. So same way, PA will be less than PA naught into chi A, PB will be less than PB naught into chi B, and delta H and delta V will be also less than 0. That is why the total vapor pressure will be less than expected from Rolle's law. And an example is solution of acetone and aniline. So remember one example for a negative deviation as well as positive deviation. Clear? Now moving on to the next topic, which is azeotrope. So you can expect this question for 1 mark. What are azeotropes? Give an example for it. Or what are the different types of azeotrope? Okay, so binary liquid mixtures. So binary means two components containing liquid mixtures having the same composition in liquid and vapor phase and boil at a constant temperature are called as azeotropic mixture. So they are liquid mixtures, okay, having the same composition in its liquid phase as well as gaseous phase, and they will boil at a constant temperature. They are called as azeotropes. So example, you can see 95% ethyl alcohol and 5% water by volume. Another example is 68% nitric acid and 32% water by mass. And now azeotropic mixture also you have two types, that is minimum boiling azeotropes and maximum boiling azeotropes. So minimum boiling azeotropes are the ones which shows positive deviations. We have already studied non-ideal solutions showing positive and negative deviations, right? So minimum boiling azeotropes are the ones which shows positive deviation. Maximum boiling azeotropes are the ones which shows negative deviations, right? So minimum boiling azeotropes, the solution which shows large positive deviation from Rolle's law are called as minimum boiling azeotropes because their boiling points will be less. Easily they can be converted into vapor phase because the AB interactions are already very less. So example is ethanol 95.5 percentage and water 4.5 percentage. The boiling point of ethanol is 351.3 Kelvin and of water is 373 Kelvin, and the mixture, that is a mixture of this, the boiling point is 351.15 Kelvin. Okay, the same way ethanol 6.8 percentage and chloroform 93.2 percentage. The boiling point of ethanol is 351.3 Kelvin and chloroform it is 334.2 Kelvin, and mixture, the boiling point of the mixture is 332.3 Kelvin. Okay, so now what is maximum boiling azeotropes then, which are having large negative deviation? The solutions which show large negative deviation from Rolle's law are called as maximum boiling azeotropes. So it is the opposite. Minimum boiling azeotropes will have positive deviation. Maximum boiling azeotropes will have negative deviation, right? Example for this is ammonia 68% and water 32%, water for 43% and hydrogen iodide 57%. Okay, so azeotropes are the liquid mixtures which are having the same composition in its liquid and vapor phase, and they will boil at a constant temperature. So I hope that is clear. So now let's summarize the difference between positive and negative deviation in non-ideal solutions. So positive deviation, enthalpy change and volume change is greater than 0. In negative deviation, it will be less than 0. In positive deviation, the attractive force between AB is weaker than AA and BB interaction. That is why vapor pressure will be more. And in case of negative deviation, AB interactions are stronger than AA and BB interactions. Now, the positive deviation ones will form minimum boiling azeotropes and the negative deviation ones will show the maximum boiling azeotropes. I hope it is clear. So in the next session, we are going to study the very important part of this chapter, that is colligative properties, from which you can expect numericals as well. Right. So there is relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, as well as one more is there, which is osmotic pressure. That 4 colligative properties we are going to discuss in the upcoming sessions. So I hope the concepts that I've covered in this session is clear for you. So that's all for today. Thank you.